Okay, and where was that? Here we go. Okay. All right. So last time we began talking about something called contextual embedding, right? And we talk about something called attention. Okay. So to demystify attention, basically attention is a function. Here I use a function between a word and all its contextual words. Okay, so the idea, so here I'm explaining the motivation behind attention is that we assume that a meaning of a word is a weighted sum of the meaning of all its contextual words, right? And you can imagine that it's quite doable. Actually, do you guys know a test called close test? I think it's called a close test. So it's something we commonly do when we were in elementary school kids. Close test. How is it called nowadays? So basically, it's this, right? So you are giving a sentence and one word got knocked out. So the teacher will ask you to say, hey, can you fill the blank? Put the right word over there. So this kind of test is called a close test, right? So you can imagine, for example, here, this missing word here in this example is the word supermarket. So why? Because we could, the hypothesis behind attention mechanism is that supermarket is a place where you can buy lots of grocery foods, right? So you can imagine that, look at the context words. He said, I went to somewhere, okay, and I bought milk and eggs. So we can say, oh, maybe supermarket is a weighted sum of the word somebody went to, buy, and milk and egg. Those are the words that determines that here is a supermarket. Would you put a hospital here? Probably very unlikely, right? Because nobody goes to hospital to buy something. Well, you probably buy some medication, but that's a pharmacy, right? Especially you won't buy milk and egg in a hospital. So, and we can see why the sum has to be weighted sum, because some words here determines here is a supermarket rather than a hospital, right? Because milk and egg, they are the determinators. For example, here, if we change this to, today I went to somewhere and bought some aspirin and bandage, that'll probably be a pharmacy, right? Instead of a supermarket. Or if you can say, hey, I bought some gasoline and a diesel, you definitely put the gas station here rather than a pharmacy or hospital here, right? So that's why it's weighted sum, because the weights means that some words, some contextual words have higher influence to the central word which you try to model. So with that example, that closed form example, you can understand why the contextual embedding is defined like this, right? So for every contextual word X and the word you try to model, we measure how strongly these two words correlate. Okay, this becomes the weights. Okay, and then we weight the embeddings of every contextual words using these weights, sum them together, and use that as a representation of the word which you try to fill in the blank here. Okay. Similarly, if in this sentence we do not knock out supermarket, but instead we knock out milk, you can imagine we can still somehow guess you will buy milk here, right? Because we can again use the contextual embedding, because you have supermarket and you bought eggs. So we know that if it's a supermarket, you buy eggs, most likely you will buy something like food, right? You wouldn't buy gasoline and eggs. You wouldn't, because normally you wouldn't buy gasoline in a supermarket. They do not sell gasoline. Yeah, so that's the idea behind attention. You can see it's quite intuitive, right? Nothing fancy, right? Yeah, I had this idea actually. I always have this idea, but I was in action really fast. So I still remember in 2017, before I learned this attention mechanism, I was talking to my friends, say, hey, I said, why don't we have something called a just-in-time embedding? So this is actually my just-in-time embedding idea, but you can see it's different from the actual attention mechanism. We'll see the actual attention mechanism. It's several times better than this, okay? But I told my friends, I have an idea. It's called just-in-time embedding. Basically, we assume the meaning of a word can be determined, is determined by the word around it, okay? And there's a weighted sum between this. That's my idea, just-in-time embedding. Later I learned, somebody already invented it. It's called attention mechanism. Already invented in 2014.
So are the weights learned or they are fixed?
Good question. These weights will be learned, okay, through training. So this F will be approximated by a neural network. So you can imagine, why do I know that, for example, here in this sentence, okay, there is a strong correlation between supermarket and milk and egg. That's through training, right? Because we speak English a lot and we go to supermarket a lot, we go buy a lot of things, and we know that supermarkets and milk, those two words, they co-occur quite often. So similarly for the neural network, we would let the computer basically memorize the correlation between words. So you can imagine, basically, this is a crazy, massive amount of neural network. So that's why later we'll talk about that, why big machine learning, big language models, they are capable of doing complex language tasks much better, because they have more hyperparameters to characterize or to memorize, you can say that way, to memorize all this information. When I was talking to a friend in about 2017, 18, I think, 18 or 19, probably that time, we had an argument. I said, I don't like your current, those big language models. I said, basically, they have too many parameters. They basically memorize it. It's because I think a machine learning model shouldn't memorize things. Because if it's memorize things, then why don't we, for example, build a co-occurrence matrix, right? Just count the frequency of all those words co-occur on a different context. But that is a very computational, inefficient approach. But then you can see that in the past few years, actually, there's a lot of papers talking about does the neural network actually memorize this information, or does the neural network find an efficient way to represent it? Actually, a lot of research show that the neural network is not the lowest level of memorization. It does actually find certain ways to remember this information, but in an efficient way. Okay, not in the stupid way, like counting beans, that kind of stupid memorize. No, not that. All right. So this is the intuition of attention, and quite often this function F, people call it energy. Okay, yeah. So when you see energy, don't get freaked out. It is energy. All right. All right. So yeah, that is actually a question. You ask a good question. So this F, is it learned or what? So yes, it is learned. So the question is, how do we let the computer learn it? Okay. Actually, I just give you one example, right? So in deep learning or in training language models, something quite often happens is that you design a task for the computer to do. And the reason is because, remember, we talked about supervised learning. Supervised learning, you need to tell the computer what's the expected outcome. So imagine, for example, you say, I want to train a computer, say, in a picture, right? From a picture, tell me what's in the picture, whether it's a car, a bird, or a horse, or a computer, right? So how do we teach the computer to do that? We'll take probably 1 million pictures, right? Then we hire 10,000 people, say, you label what's in this picture. That's the way to do it. But that's very costly. Obviously, you can imagine it's very costly because you hire so many people to label it. And so in NLP, researchers take a different approach. In NLP, something quite common is called self-supervision. Self-supervision means that I already have the corpus, I have the text, and I change the text and ask the computer to do something related with the task. And then the computer can learn. And that's good for for us, because I do not need to label the data. Instead, I just need to write a simple program to do it. For example, here, the close test is a very common task that people use to train a language model. It's very simple. You take a bunch of corpus, right? And you randomly knock out the words and ask the computer to predict the knocked out word. Right? So this thing is actually, there's a name called language model training this. It's called a masked language model. We'll go into details later, okay? So what generally is, basically the word got knocked out, we say it's masked out. So which means this word got masked out, which means the computer does not know what that word is. And then we want the computer to reconstruct, say what was the word that got masked out. Then through this, we could train it, right? We just seen the example, right? We can use this approach to force the neural network to come up with a weighted sum representation of the knocked out word based on its context, right? So therefore, through this, we could train this function f. I like your jaw-dropping facial gesture. That means, oh, you got to blow out. Yeah, this is so smart, right? Don't you think this is super smart? We don't have to label the data. We just write a simple pre-processing script and let the computer do the whole thing itself. And you will see that we can train the computer to do anything we want, actually. We'll see lots of examples. I'll show you lots of examples in the next 2 or 3 weeks. We can let the computer do anything. It's crazy. There's one more thing called a give you a sneaky bit called a prompt. That's even crazy. Okay.
How can we know that you did it correct?
Oh, you know, because you masked out the word supermarket. So if the computer was giving you an answer of other words, you know it's wrong, right? And so if the computer gives you a prediction and you know the ground truth is supermarket, we have difference. And we know that with difference, we can have the gradient. With gradient, we can update the neural network, right? But, well, I'll show you the joking a bit while we're having a break. All right, so let's see what we do it, okay? The attention mechanism is first used in the machine translation. I need to tell you a little bit. So the attention mechanism was actually not first introduced in NLP. It was first introduced in computer vision. But it turns out it became really famous in NLP because NLP is really a place where attention mechanism can bump up the performance a lot. Okay, it was crazy. All right, so let's talk about this problem called machine translation, okay? So obviously there are two approaches to do machine translation. One is rule-based system, right? You first do word-to-word translation, and you have a bunch of rules to say, how do I order this word in this language to words in another language to do that kind of thing. That is obviously not scalable. So here we're talking about neural machine translation. We completely use a neural network to do the translation. All right, so we talk about some work. The first milestone work, which I already talked about, I mentioned the title of the paper, right? Is where the encoder, decoder, and attention mechanism got really famous. Is this paper? Okay, it's called a neural machine translation by jointly learning to align and translate. Okay, you can see the footprint or the track, the mark of machine translation, right? Because a problem in machine translation is how do you align words in two different languages, right? That's something really important. And it's very difficult sometimes because in some languages, the order of words flip, or in some languages, even the whole clause has to swap their orders. That's difficult, okay? And then in 2017, Google published a paper, a very famous paper that made attention got people's attention, okay? This paper is called Attention is All You Needed, okay? We will see this paper. In this paper, Google reviewed something which is now a buzzword in AI. It's called a transformer. Okay. All right. And we briefly talked about the encoder decoder architecture, remember, in the deep learning part. So let's quickly brush up our memory. So encoder decoder, basically, it's a neural network with two parts. The first part is called an encoder, right, which we encode a human readable information, such as a picture or a text, into a vector representation, or sometimes people call it a latent representation, okay? And then we have a decoder. Decoder basically generates the output based on the latent representation, which is usually compact, contains the most essential information needed to reconstruct the data, the information, okay? So those two, we put them back to back, became an encoder decoder, and the input and output information can be in the same domain or different. For example, in machine translation, you could argue that the input is in one language, the output is in another language. Those are two domains, but they're both text, okay? Another thing, which is I showed you the Dolly thing or the stable diffusion demos, right? The input is a text, the output is a video or a picture. That's even crazier. All right, so skip the examples we talk about. And we talk about what is autoencoder, right? Basically, the input and output is the same thing, so that's called autoencoder. All right, so let's talk about a general framework which people use to do machine translation, which is called sequence-to-sequence learning model. So this approach was introduced in NIPS 2014 by all these gurus, okay? The three of them, they're all gurus, okay? This is not from their paper. This is from Google's TensorFlow tutorial. So, and we already briefly talked about how such sequence-to-sequence model works, right? So in the encoding stage, we have the sequences, what the input sequence, okay, in this sequence, every element of the sequence is a word, right, or a token is encoded, okay? And then, okay, so we have the encode, okay. Let's see. It takes inputs in, yeah. So it will first do the encode, okay? In encode, it goes step by step. Each step, it adds one input token into the encoder's hidden state, okay? All right, and then a special token will trigger the decoding stage. So here we say we have this special symbol says the input sequence has finished, so it will start triggering the output, okay? So we talked about this picture, right, when we were talking about RNNs. So such a sequence to sequence, because it encodes it takes one token as input in each step, and it generates one token in one step. So obviously, this is quite frequently implemented in RNNs. For example, we can use a vanilla RNN, or use LSTMs, or use GRU networks. Okay, all right. Interestingly, is that the input and output sequence, they could have different lengths. Okay, so for example, in English, you say, do you speak German? It takes 4 tokens, while in German, when you say, do you speak German? It takes only 3 tokens. So this architecture does not require the input sequence and output sequence to have the same lengths. Okay, and machine translation is particularly difficult. For example, between English and Chinese, that's very difficult, because in English, every sentence can only have one verb, okay, while in a predicate. While in Chinese, you could have complex sentence quite often. So something very interesting is that in English, one sentence, you have to break down multiple sentences. When you translate them into Chinese, you have to combine them into one complex sentence, or the other way around. So you even need to break sentences. That's more challenge, okay? But that's beyond the scope of this class. So we're not going to talk about it. All right, so let's look into the details of the encoding stage. So in encoding stage, I have a bunch of tokens, right? I have many tokens, and I will build an RNN, right? Okay, and remember, we talk about RNN. RNN's input has 2 parts, the fresh input and the hidden state from the previous time step. Combine these 2, you compute the new hidden state of the current step. That's what you have, okay? And we use this notation, for example, because we have n input sequences. Okay, so you can imagine this RNN will advance n times, the capitalized n times, right? Okay, and lastly, we use this notation H capitalized N to represent the last hidden state of the input sequence of the encoding step. Okay, remember when we were talking about the TensorFlow API, there's an output and HN and CN, remember? Ah, you guys forgot. Remember the output? This one and this one, remember? Why is that? So this is the hidden state after you pack everything into a RNN. Okay, so this HN is this HN, okay? That's it, okay? And then you have the special token to trigger the decoding. So the decoding stage, why my compilation didn't work? All right, this error. Don't forget, I was trying to fix this typo earlier before the class. So the decoding RNN is a bit different, okay? The decoding RNN not only has the output at the previous step. So you can see, quite interestingly, we talked about last time, right? So in the decoding stage, the input is fed from the previous step's output. So this output, this becomes the fresh input of this RNN, okay? But not to be confused, also, the RNN has the hidden state of the previous step here. So not only does it have the fresh input and the hidden state of the previous step, this RNN also needs to factor in the last hidden state of the encoding stage, which is all the information I have. that needs to be translated. So you can imagine all the information needs to be translated is here. Okay, sorry about the typo, which I failed to fix, which is HN. Okay, this is all the information that you want to translate, encoded in, for example, here in English. And this is the token generated in French in the previous step. And this is the hidden state of the decoder. So these three together be fed into a neural network and being mapped into the new hidden state of the decoder. Okay. You might ask, so you have two stages of this RNN. So what does SM stand for? Well, in here, then we can imagine that we have two RNN. So this SM will be used, this one will be used to build one of the RNN unit, right? Because this corresponds to this RNN unit at the bottom one. Because for the bottom one, the fresh input is a word got translated in the previous step. While for this one, its fresh input is actually the output from the first RNN unit, okay? And the hidden state, okay? And for this second RNN unit in the decoder part, then its HN here is the HN of this RNN unit, okay? Not the HN of this RNN unit. Questions? Okay, all right. All right, so lastly, we need another function, so which is this golden part, okay? We need a function G to map the hidden state of this decoder to an actual word in the target language that you want to map to. All right, so with attention mechanism, let's see how attention mechanism works. So the attention mechanism we talk about is basically a word which you care about. Let's call the center word and the contextual word. So in machine translation, quite often what happens is we have let's say this is my center word, okay? So this is the first center word I try to generate. So I will compute its attention weights with all the previous history words, okay? So all the words in English became its context, okay? And we compute a contextual embedding of it. Now you can imagine why it will work. Because all these English words are together with the knowledge that this is the beginning of the sentence, we will get the attention. We will steer, you can see this example actually is good. It just steers the attention to the word I. Basically, it tells this neural network, the first word you translate into French needs to focus on the English word meaning I. Okay, and you can imagine in the next step, what does this word mean in French? Literally, if you translate back into English, M, right? So you can imagine when we compute the attention between this hidden state and all these English words, we will see the highest attention weights here, right? Because we want to tell the neural network, hey, now you should steer your attention to the word M to generate the word in French corresponding to the meaning M, right? That's how attention mechanism could help machine translation. Any questions? Okay. I can imagine it's not hard, right? You can code up this in 30 seconds, right? It is, you can code up in 30 seconds because now the deep learning framework is so easy. Just this one line of code. This one line of code. That's it. Attention, another line of code. That's it. 3 lines of code, you have the neural network. Okay, all right. So then let's talk about another work, okay? So this one is the sequence-to-sequence approach. And let's actually, when they publish this paper, they do not have the attention mechanism, okay? So let's see how when the attention mechanism is used. Let's talk about this paper called RNN search, okay? So obviously we can see attention is needed, okay? Because you want to steer to know that now I'm going to translate one word in French. What are the English words which I should focus on the semantics on the most? Okay, so for example, and so we need attention, and we should notice that the attention is context-based, okay? So the attention you need is different. Actually, I just give you one example, right? So when you try to translate the first word in French, you need to steer your attention to the English word I, while for the second one, you want to steer your attention to the word M. So here I have another example. So the weights of the context should differ depending on the output word, okay? So for example, let's say if you translate the word sprechen okay, then your attention, your focus should be on you rather than German, because that's how the grammar of German works. Okay, so in English, after you say, "Do you speak?" Okay, where's my example? So, for example, let's say you translate German to English. Okay, if you translate German to English, now you generate the word "speak." After you popping up the word "speak," you need to know that the next word I should pop up to should correspond to the German word Deutsch, right? But when you go from, for example, you go from English to German, after you pop up the first word sprechen, you know, okay, I need to find the correspondence of the next word in English, but I should focus my correspondence to the word you rather than du or German. Okay, so you can see the attention needs to be changed depending on what you are doing or which stage you are in translation. Okay, all right. So therefore, this is how this RNN search work they do. Okay. So first of all, they do not use this hidden state. Okay, as so remember what is this? This is the hidden state of all the input information. Okay, so instead in this paper they change this to this. Okay, this means that the representation of the input depending on the decoding stage M. Okay, so which means that they will compute a vector on the fly to know that what involving the information of both the input sentence in English and the what has already been pumped out in German, for example, in this case, or in French, whatever language. So this thing they call it context vector. And how do they compute the context vector? They just leverage the attention mechanism. Okay, so what they do is they try to compute the hidden. So this is the hidden state. In I think I probably messed up. Yeah. So this M is used to represent the output sequence. Okay. So did I mention? Yeah. So the N is used to, so this should be HN actually. So the subscript N is used to decode the index in the input stage, while the subscript M is used to represent the steps in the decoding stage. Okay. So in order to compute the contextual vector, what they do is for every hidden state, for every state in the inputting stage, they compute a weighted factor. Okay, basically they build a one-to-one correspondence. So which means that in this example, what they did was, let's say I am at this step, okay, the je step, okay. So what they will do is they will compute the attention from every hidden state in the input stage to what has already to this hidden state of je, okay. And the next time when they're going to translate, when they're going to pop out this word, they will use this hidden state and then compute the attention between this hidden state and all the input hidden states. Okay, I think I'm being a little bit repetitive, sorry, because I already explained the intuition earlier, right? Because I said when we were translating this word je, we want this hidden state, we compute this hidden state's correlation with all this input hidden states, right? And for this one, we computed this hidden state with all this input hidden states, and we want the highest weight to be focused on M here, while here we want the highest attention weights to be focused on the word I. So that's their idea, okay? And then they do a softmax to normalize everything. That's it.
Why doesn't it learn the attention of the French of the outputs?
It learns. Yeah. So remember, this alpha it's learned through a neural network.
But it's from the input language, not output.
Oh, it's output. So you can see this HN is this is the input part. Okay. So it tries to learn the weights. So, but you have the M here, right? You have the M here. M is the output stage. So you can see here we're learning the attention between this hidden state in French with all the hidden states in English. Next time, you will learn another set of attentions between this hidden state in French and all these hidden states in English. So this attention weights is across two languages. I'll show you a picture later. I have another picture later, actually, from this paper, okay? So it does. And you can see this attention is language dependent. You train this language from English to French, that's one set of weights. You train this from English to German, it's another set of one. English to Chinese to Korean to Japanese, that's a different ones. Yeah, it's all different, it's all language dependent. Other questions? Good. I like your question though. That means you're listening. Okay. All right. So you can see this network alpha. So this attention weight is normalized. Okay, this is the brilliant. This is a new network. This is the F we just talked about. Okay. So this network memorizes the contextual dependency across tens of thousands of words across two languages. Okay, because you can imagine in this case, in this step, it needs to memorize, okay, the hidden state, of course, this is, I don't have a good example here, but this is a hidden state, says all the words in French, nothing has been translated yet with all different English words. Okay, you need to memorize that. Yeah, so that's what this attention network is. You can imagine attention is something similar to embedding, except embedding is about a single word itself, while attention is a representation of the any two words, any pair of two words, you can compute an attention.
You can set the window of how long we need to go over to learn.
Yes, that's something we'll talk about. That's why, for example, many pre-trained language models, they have a length limit. Some of you are doing the project, you're using BERT. For example, you say, hey, why do we can only have 512 tokens, right? Because you can imagine if your input sequence is very, very long, let's say I say a super, super long sentence, that's 10,000 words. So how many alphas do I have to compute? I need to compute 10,000 pairs of input hidden states and every state in a translated sentence. So this will increase quadruply. That's going to be really crazy. So that's why we have this length limit on language models. Okay, so this is how much you can go. Beyond that, that's going to be too crazy. Forget it. Yeah, you see. So this is how it works. This model. This is a picture I took from a different people's illustration of the original paper. Okay, so this guy. So this in this example, want to translate English word "How are you" to Korean. Does it say "안녕하세요" here?
Yes.
What does it say here? What does it literally mean in English? Huh? Okay. All right. Okay. Anyway, so to answer Tim's question, yes. So you can imagine, first we do the encoding stage, right? So which means you do not generate anything in the output. You pack one word into English each time. Okay. How are you? Okay. And then you go to the translation stage. So translation stage, first you have the initial hidden state in the decoder. Okay, so at this point, the decoder has not yet output anything yet. Okay, so then we compute the attention between all these three attention mechanisms. Sorry, all these three hidden states and the first hidden state of the decoder. We get a bunch of weights. Okay, then we generate the first token in Korean. Okay, so then we feed this in the first token generated to the decoder again as part of the decoder input, and you can see there are two arrows. So this is the fresh input, while this one is the hidden state carried out from the previous step. Okay, and then over there, what's going to happen? You can imagine. I don't have an animation here. Then you will change the arc from these three encoder state to this hidden state of the decoder. So you can imagine it's different. We change them. Okay, and you can imagine because this hidden state and this hidden state are different, because this hidden state know that the first token has been generated in Korean already. So that's why these two hidden states are different. So the attention mechanism needs to memorize that after this piece of information has already been decoded, my attention between this hidden state and these three English words probably should change. Okay, so for those of you who speak Korean, what does this word mean literally in English? Well, it means doing well. Okay, all right, that's I just want an example. I don't care what that is. I just want one example. So you can imagine, after this hidden state knows that doing well has already been outputted in Korean, this hidden state probably should change, right? For example, we should change to you, right? Because you know that when you say how are you, well, this is a bad example because how are you doing is such a general phrase in English, right? Because how are you doing could mean how well you are doing, right? So after how well has been outputted, we can know that in this sentence, we also have another set of information we want to encode is you, because I could say, how are you doing? Or how are your students doing? How are your car doing, right? So that's why in that case, the attention should focus on, so you can imagine, team, if we could visualize this attention, that in the second hidden state of the decoder, this attention will be highest. So I note that this attention will go from here to here, not again from here to here, okay? We want this attention to go from the 3 input hidden states, or the 3 hidden encoder states, to the second decoder hidden state. Okay, so that, and because the attention focus on you, the next few words translated in Korean will focus on you rather than your car, your friend, your house, your parents, those kind of information. Okay, now you can see why attention mechanism can be useful, right? Quite intuitive, right? Okay. Yeah.
I was wondering, these input layers, are they really like implementation of the network? Are they really real layers, or are
They're real layers.
Are just the same layer in this thing?
They're the real layers.
For example, here we have 3 layers.
Oh no, we don't have 3 layers. It's the same RNN in 3 different time steps.
Okay.
Yeah.
The encoder and decoder based on 2 separate word embeddings.
Yes, you need, yeah, that's something we ignored actually. So obviously we need word embeddings, otherwise they can't function. So we will have embeddings for English and embeddings for Korean. Yeah. Good question. Any other things? Okay, all right. You can see this is another NEEPS paper. What's the difference? It just leverages the attention mechanism, okay, and let the decoder generate the output not based on the fixed last state of the encoder, but rather than it uses the attention mechanism to do it. That's it. That's the difference between this one and the earlier one by Quy Le. I don't speak Vietnamese, but I assume that's how to pronounce his name. Okay. Any other questions? That's why America is the best place to learn NLP. You can find people speaking any language in this classroom on our campus, right? That's cool. All right. Okay. All right. So here we talk about attention. This is called unidirectional attention. Okay. This is one directional attention because the attention is always from the hidden state, the encoder states to one state in the decoder. Okay, so this is good enough for machine translation actually, but in many other cases, it's not good enough because you can only look at the attention one way, but not the other way. Okay, in many cases, we want to look also the other way. Okay, but in machine translation, you do not need to look back because you're not generating English from Korean. So you do not need to look back. You do not need to look at every state in Korean and this attention weights to a state in English. You do not need to look backward. So sometimes you need to look backward. So this thing is called a bidirectional attention. Okay. So the bidirectional attention usually works like this. So first of all, you have RNN. This RNN goes, actually bidirectional attention is because the underlying RNN goes bidirection. Okay. Because here our attention goes one direction, right? The English goes left to right. The Korean goes left to right. So sometimes the LSTM or the RNNs, we can have something called a bidirectional RNN. So basically, it's the same thing, except that depending on how you input the input sequence. So if you're feeding how are you, you go forward direction. You can also feed backward. You are how, that's backward. That's it. That's what we mean by bidirectional. So this one is how are you? This one is you are how. That's it. Okay. All right, so let's go into a little bit difference. Why this is useful, give you an intuition why this bidirectional thing can be useful in NLP. For example, in machine translation, usually actually the word order really matters. Okay, so you need to look ahead. So, for example, when you say "Sprechen Sie Deutsch," but in English we say "Do you speak German, right? So to tell you a little bit, so sprechen corresponds to speak. You can tell from the spelling similarity. But when you generate do you speak, you need to know that I want to say do you rather than speak, because you could ask does he speak German, does she speak German, right? So but when you translate it into English, you need to look ahead. So how can you look ahead? You could use this bidirectional to look ahead, basically. So the symbolism is to train a bidirectional language model. This is the bidirectional language model. Okay. So usually people use this notation. So note that here, this arrow above a variable name does not mean a vector. It's a abuse made by deep learning people to say, hey, I'm talking about an RNN in which direction. So you have RNN left to right and RNN right to left. You have these two. And these two concatenated them together. So here you can see there's no arrow between this one and this one, okay? Because we just concatenated them, we just band them together, okay? All right, we'll band them together to become a hidden state, and the rest of it is the same. We computed the attention weights as using a neural network, and we do a softmax normalization. That's what we do. Okay. This is for the encoding stage. Okay, encoding stage we do bidirectional. Okay, but in the decoding stage, of course, we go left to right because there's no need to insert a word on part of a sentence that's already been translated, right? Okay, so how do we compute the A? So this attention, the attention weights is actually a function between the encoder state and the decoder state. Okay, so note that they're not on the word embeddings. Okay, that's the difference between my original superficial idea called just-in-time embedding. So remember, in this intuition, I told you I'm talking about the these one. They are the embeddings of words, right? So, and in reality, when people use it, they do not use the word embeddings. They use the RNN's hidden state, and you can see why that is useful. Why it's better? Because RNN's hidden state contains also the ordering of words, like how those words are fed into this neural network. So that's more meaningful than simply computing the weights between I's word embedding and Ju's word embedding and M's word embedding and Ju's word embedding. So instead, we use the hidden state. We compute the attention over the hidden states. That's something I want you to pay attention to. Okay. All right, so how do we compute it? So there are actually several ways to compute the attention. So one way to do that is we build a single neural network like this, right? So remember, this A, we want it to be a neural network. So, and in the, for example, let's say this is a hidden state in the decoder stage, right? This is a hidden state in the encoding stage. So how do we do that? We can use a single neural network to do that. So this one is made, this approach is called additive attention computing. So you can imagine, so first of all, the decoder state, the decoder hidden state got to a linear transform, right? So this W1 is a transfer matrix. And then the encoder hidden state is also linearly transformed. And so these two together, they got added together. That's why we call additive attention, okay? They got added together. We pass them through an activation function, okay? So note that this one is a vector, right? Because this is a vector, this is the matrix, so this is a vector. Similarly, this one is also a vector, so these two added together is also a vector. So although we pass them through an activation function, this whole thing we got is a vector. This is a little bit different from what we did in each neuron, right? Remember, in each neuron, you have an input, transform, you do dot product, so you become one scalar. So therefore, after you pass through the activation function, it becomes a scalar, okay? So this whole vector is dot product with another vector, okay? And then we got our attention. The attention weight is a scalar, okay? So this is called additive. And then there's another one, which is called a multiplicative style attention, okay? Which does not add these two parts together. Instead, they have a transfer matrix to connect these two. So again, this is a hidden state. This is the decoder's hidden state, while this is the encoder hidden state, and they use a matrix to connect these two together. This is invented by Laws and his co-authors. Okay, so therefore, when you look at papers, you quite often see these kind of things. I took this picture from a paper. Okay, and there are some other notations. Yeah, so you can see some other notations. I use these variable names. There are some other variable names, but they're pretty much all the same. Okay. Okay. So far, these attention mechanism we discussed is called single head. You have a question? No? Okay. It's called single head attention. Okay. Which means that for every pair of hidden state, for example, for every pair of decoder hidden state and a encoder hidden state, I just compute one scalar. Okay. Experimental results show that we could allow between every pair in the decoder hidden state and the encoder hidden state, we could compute different pairs of such attention weights. And such attention weights will memorize different things of natural languages. Okay, so for example, one attention memorizes polarity, one attention memorizes gender, and the other attention memorizes tense. Okay, you can imagine that could be useful when you want to translate one word, for example, you to a different languages. You need to have all those kind of informations. So if you spread them out on different vectors, that'll be much better than containing them together. But of course, you probably ask, how do we make sure that one attention is on gender, one attention is on polarity, one attention is on tense? No, we cannot control that. It's just a hypothesis. Just like in word embedding, we assume that those dimensions, each of them correspond to different semantics, different meanings. So, and the empirical results here show that indeed, if we allow between every pair of this decoder hidden state and encoder hidden state to have different attention weights, we can do much better. So the empirical results can be much better. So this thing is called multi-head attention. That's it. Basically, you compute different A's given a hidden state in the encoder and a hidden state in the decoder. You compute different A's. You train different neural networks to do that. So you can imagine in this, yeah, that's why the multiplicative side is easier. Basically, we want to train different W's. Okay, we can assume one W connects one word in English, connects the hidden state in English and the hidden state in French on the tense. The other W connects, for example, a polarity, those kind of things. It's called a multi-head attention. All right. And you will see this abbreviation MHA. That means multi-head attention. Yeah. So basically, we want to distribute the attention to different scalars. All right. Take a break. Yeah, let's take a break. Let me show you something. On my Twitter. Again, I don't want you to see my Twitter. Well, I'll let you see my Twitter. Oh, come on. So this is a fake picture. This is generated by AI. Of course, I'm not a female. All right. So this one. This is what I saw. Okay. Aha. This is what I was doing in June this year with Alex, but so you can look at what no, sorry, this is what I want to find a copycat. Then I need to disable screen sharing, and because I want to go to my chat log with Alex and we talk about other things. So can you send me the link? The one they use GPT-3 in Google Docs.
Oh,
Yeah, come on, send me the link. Yeah, but I stopped the screen sharing. Yeah, so that's fine, right? Let's see.
oh,
No, not this one, not this one. The one using GPT-3 in Google Docs. You shared in your group and you added me.
oh.
You got it? Okay. Let's see this. Yeah. Okay, good. This is the one. All right, let's see. Every day there's something new about NLP. What the heck is my Zoom? Hold on. I think my Zoom crashed. You cannot minimize Zoom when you are recording. Okay, sorry. Give me a sec, guys. I need to reset the monitor. All right. It's not working, the monitor. Yes, okay. All right, okay, share screen. Okay, all right. So see this demo. Someone posted a couple of days ago. Well, how do I make the full screen? Okay, all right. So you can see what he does. Let's go to the beginning. So he has a spreadsheet. Okay. Now, and quite often we want to do some tasks in spreadsheets, right? One way is you write a function. But here, this guy, he used GPT-3 to do it. So he says, I have the address in this cell. He will select this column, okay, A, and he will ask your GPT a question. What state is this address in? And he even give a further instruction, say, answer with 2-character state abbreviation. And let's see what's going to happen, okay? Ta-da! See, GPT-3 understands this is an address and realize the state is Massachusetts, and even further understand his instructions say represent the state in the 2-letter abbreviation, so it becomes MA. So you can see here he has a mixture of 2-letter abbreviation of states and the full like state names, and he will now drag down to show you. Oh, now he went on to do a different one. Okay, to do zip code. What is the zip code? Okay. Oh, now he would come on, drag it down, drag it down. Yeah, good. Is that crazy? See, California becomes CA, Maryland becomes MD, and if it's originally in the abbreviation, then it's copied here, right? But you see something interesting? It thought Philadelphia is a state, while Philadelphia is actually in Pennsylvania, right? Yeah, but it works pretty much very accurate, right? You can see, and you can see there are a bunch of numbers, and GPT-3 because we write address in this quite oftenly, so GPT-3 is able to learn that the last 5 digits is usually what is something we call zip code. So when this author asks GPT-3 to extract a zip code, it can extract the last 5 digits rather than any other numbers in a street in this document. However, I doubt that if you use a different instruction, for example, say extract the street number, it'll probably get lost because zip code is quite often mentioned, while we do not explicitly mention, for example, this is a street number, right? So that means that GPT-3 wouldn't have the training data to do that. All right, let's move forward a little bit. Oh, and this is even crazy. This one basically, take a look. I'll let you take a look. His instruction first. Okay, so he says, guys, I want to. Basically, he says we are writing a thank you card to them for attending our wedding. Okay. And he said, please write 6 or 7 sentences for the card addressed to them. Be sure to mention something in these things to mention. Okay. And he says what model to use, the temperatures, maximum number of tokens. So basically, it's a use case where somebody went to your wedding, right? And I want to mention, I thank you for what? Thank you which family for what? Okay. And let's see. I really love this feature. I'm really tired of this kind of chore, which I have to do because I don't do IPS of people. But if I do it, costs me a lot of time.
It completely generated by a computer.
Yes, by GPT-3. You want to change your major to computer science now? See, look, and it's really smooth. No, the first one says, thank you so much for attending our wedding, for the lovely gifts you gave us. The flowers are beautiful because they mentioned the flower. The card is very thoughtful, and we really appreciate the 500 donation to our favorite charity. Yeah, and then a bunch of your template, boilerplate thing, right? We're so lucky to have a supportive, generous family, friends. Thank you again for everything. We're really grateful. Ta-da.
We used to write our SOP,
Give it a try. But I doubt because I know GPT-3 cannot generate really long. Once you generate really long, the content drifts too much. So do not expect you to begin one sentence once upon a time in the galaxy far, far away, and it will write you the whole what's called a script of Star Wars. No, that I don't think that's doable. Okay, but yeah, for shorter messages, it's great, right? Yeah, so the second example, things to mention is the dance went well and they carried the cake to the hall. So you can see GPT-3, does GPT-3 mention the dance? Yeah, see, we had a blast dancing the night away with you all. We definitely know how to get a party started. Wow, it even knows this. It says the dance started the party, okay? And then, oh, you carry out cake into the hall. What a perfect way to end the night. Geez, how does GPT-3 know that during a wedding, you use the cake to end a party? No, you don't end a party with a cake, right? You end a party with party after party, right? I'm just kidding. Okay, all right. Crazy? Yeah, this is all powered by attention. So and you can understand with attention, basically GPT-3 is a huge language model, and it's unidirectional. And but it has crazy number of parameters. Okay. Yeah. And interestingly, okay, I should have made this joke in the middle of the class. Yeah. So now it's kind of late. Now let me tell you something really interesting. I was scrolling down to see how people responded to this because I want to see whether people say they use Excel, they need this, or they use Google Docs, they need this. And then I found an interesting reply. Let me search whether I can find it. How come I can't use search? Oh, here we go. Oh, it got deleted. Okay, so then I found this company through the reply. Actually, the co-founder of this company says, I saw you signed up last week. Did you get inspiration from us? Basically, I think he's planning to say, you stole the idea from me. And this company was doing something pretty much exactly the same as what I wanted to do originally. You can see this demo. Basically, a bunch of text. They label a little bit, and then they drag down. Basically, these are the training samples, and then they train. So you can see, again, this is sentence training labels, and it will predict the rest of it for it, purely based on large language models. See, drag, predict, down. See, it can even predict which, yeah, this is not a pic, this is like a, I can't pause it. Anyway, sorry, I can't pause it. But you can see, it says positive about what? Positive about what? It will tell you positive about what, negative about. You can imagine that you can use that for customer feedback. If someone comes to your restaurant, right? You want to say whether this feedback is positive or negative about which aspect. You know, whether the food is tasty, whether the wait time is short enough, whether the service is good, whether the restroom is good, anything else, right? You can categorize it. But seriously, I had the same idea several months ago. I was really not sure how can somebody really use it. Because, for example, let's say I offer this to a small business owner. Okay, he could use it to filter out the user feedback once. But how often would he use it? He probably use it only once a month, right, to look at the author feedback. So how willing will he pay money? So my question was, how can we turn this into a paid service rather than something people will use very infrequently? That was my question. But I assume they probably have figured out. And this startup, it's backed by a very famous incubator of venture capitalists called Y Combinator. Okay. I want to give you a round of advertisement. I'm not taking money from Y Combinator. Y Combinator is founded by a bunch of really good entrepreneurs. They became super filthy rich in early 2000s or 1990s. They have really good incubator programs, and I know many good tech startups were incubated by them. They have spring and fall camps. If you have really cool business ideas, I strongly recommend you apply to them. You will learn something which you can never learn from me, okay, or any professor on campus, because they're really veteran entrepreneurs. They have seen tens of thousands of startups die, okay, so they know at least some ways you wouldn't die. Y Combinator is really cool. Y Combinator is founded by a guy called Paul Graham. Remember I showed you the naive spell checker algorithm? It was written by him. He was a list programmer, Paul Graham. You can take a look at that. Very cool. Y Combinator incubated pretty much all the companies you have heard about. Dropbox, You can see, yeah, this is so Y Combinator, yeah, starting in 2005. It's not a conventional VC because this guy was founded by Paul Graham. He used his own pocket money, so it's not like a big fund with tons of money, like hundreds of millions of dollars. No, he doesn't have that much money. So they incubated Airbnb, Coinbase, Cruise, the self-driving one. Who knows whether the company will shut the door soon. DoorDash, Dropbox, Instacart, Quora, Reddit, Strip, and Twitch. All of them. Yeah, so this is really interesting. Yeah. So cool. All right, enough jokes. Now let's go back to how we can be filthy rich. All right, go back to this. So another kind of attention is called self-attention. Okay, so you can imagine why it's called self-attention, because in here we are talking about attention between not self, right? So this is attention between Korean hidden states and English hidden states. Okay, so it's two kinds of hidden states. Another kind of attention is called self-attention. It's between the same kind of hidden states, but just different time steps. Okay, so this self-attention mechanism made the Google paper "Attention is All You Needed," the transformer architecture, really powerful. Okay. All right, so let's take a look. I do not want to talk. Let's talk about the pictures. Okay, and you can see how Google make this prediction. Now you can understand how does Google make this prediction, right? Because next word prediction is very similar to machine translation. So Google could do that and they use attention to predict attention is on it. So this is a very famous paper. You can see this paper has been cited what? That's crazy. Okay. 56,000 times. Okay. In what? In 5 years. Okay. Basically every year they got 10,000 citations. So if we look at figure 3 and 5, it's in the appendix. Get rid of the appendix. No. Let me. Oh no, I don't want you to see my email. Don't see my email. That's really with some students. So they have an appendix. The appendix, they visualized the attention actually. There's a very good. Yeah, good. All right. So let's see the self-attention. Okay, so this is what we mean by self-attention. Where's the menu to rotate? I want to rotate this picture. No, this is save. This is high. Oh, here we go. All right, so see this example. So self-attention means that it's the same document. Okay, you just let the every hidden state get every hidden state attention with all other words. So here they visualize the attention. So for example, let's say the word is making, okay? And they visualize what are the words that have the highest attention with the word making. You can see it's more difficult. Okay, and of course, making and making itself has a higher attention. Okay. Any questions? Do you see something interesting? Why do we have different colors like Lego here? Actually, I forgot this detail. But I assume it means different heads, different attention heads, I think they mean. Yeah, see, different color represent different heads. Yes, it means different heads, okay? All right, see another example. See, the law, right? So if you focus on it, its attention is with law and application, okay? And interestingly, you can see, because these two different colors represent different heads. So in this attention dimension, you can see the word law and application have pretty much the same attention to the word it. But when it comes to another dimension, only law has high attention with the word it, while application does not have it, okay? And here they visualize for every word what are the different pairs of attentions. You can see, for example, law is highly attended with the word the, law itself, and it, okay? Some word only have high attention over itself, right? Yeah, but you can see my, in this example, the word my has high attention with in my opinion, because this in my opinion phrase probably they usually come together, right? Very often in English. Okay, so this is self-attention. Any other questions? Okay, let's go to the other one, the play mode. All right, so let's see how this attention mechanism can be used to do something, okay? So one task in NLP is called MRC, okay? Machine reading comprehension. Machine reading comprehension is under the banner of the problem question answer, short as QA. So for instance, in machine reading comprehension, there are usually two kinds of input. One is called the passage, which is in the black color here, which is basically you read a paragraph, and then you have the question, then you want to generate the answer, okay? So you can imagine, how can we use the attention mechanism to train a network to do this? For example, let's say the question is, where is the apple? Then we want the attention to be steered to, in this example, Sam and picks up, right? And we wanted the attention to be then transfer from this sentence, Sam picks up, into the previous sentence, which is Sam walks into something. And then you want to put attention between kitchen and Sam walks, right? So you want to know, probably you can ignore this predicate. You want to know that it's Sam and apple and Sam in some location. So then you can build a correspondence between apple and the kitchen. Oh, sorry, I was wrong. Are you guys following? So apple was in the kitchen, right? But Sam walks into the bedroom and drops the apple. So the apple should be in the bedroom, not the kitchen, okay? I was wrong. I tricked you. Okay. All right. Yeah. So, and usually we'll see something interesting is you look at those QA papers. When you have a question, okay, you can train the computer to know where the attention is. And you want this, you will realize that if we do experiments, gradually, this question's attention will be focused on bedroom. That's how you can use the attention mechanism to find the answer. Basically, you train a neural network to say where the greatest attention is at, and that is the answer. Okay. Similarly, here. Okay. For example, Brian is a lion. What color? How do we answer this question? Brian is a lion. What color is Brian? White. What? A lion's white? Oh. Yeah, but here's the assumption, right? All lions are of the same color, right? Okay, all right. But anyway, we can use attention mechanism to do it. Usually people want two embedding matrix in this case, okay? So you can see you need attention for two things. First, you want an attention within the passage itself to learn the attention. Second is you want attention to learn the output, okay? You want attention to tell you the output. All right, so this comes to a very common case where people model attention using a formalization called KQV, key query value, okay? So what they want to do is, in the QA case is that they let the passage be the key, okay? And they have some information to be queried, which is the question, okay? So the passage is the key, the query is the query, okay? And the output is the value. So this formalization is basically from from database, right? So in database or dictionaries, we have this KQV formalization. All right. So, all right. So you can take a look at a very interesting paper in NLP 2015. It's called end-to-end memory network, okay? And then the output representation is called a value. That's what we have, key, Q, V, those three things, okay? And we want to use separate attention models for K and V, okay? Usually people use separate attention models for K and V. All right, I want to skip this a little bit, okay? Okay, so next, then we have this crazy thing called the transformers, okay? Transformers is a paper published by Google and NLP in 2017, okay? Basically, the transformer is technically, it's a network built on top of the attention mechanism. It's actually the structure is very simple. Basically, you have positional encoding. We'll talk about what a positional encoding is probably next time. I don't have time for today. But basically, they have the input, right? The input information, and they do self-attention. Basically, you have an encoder RNN, you input one token, and you do the self-attention between all the tokens, between all the hidden states. Each hidden state corresponds to one input token, right? And then you connect with a feed-forward network. That's it. And then this is your encoding stage, and you have the decoding stage, right? You have the decoding stage, and the decoding stage where you will do the masked attention for the decoded all the states in the decoding stage, self-attention again, and you have a cross attention between the decoded stage and their attention computed and the encoding stage, and you finally generate the output. This is the transformer architecture. I'll just give an overview this time. Yeah. All right. And in this transformer paper, Google showed that with this architecture, you can nail any NLP task, whether it's translation, whether it's the close test, whether it's question answering, or whether it's something else. Okay, and this led to another work, which we'll talk about in a bit, called a BERT. Probably you know what's the modern thing, right? And with BERT, probably in your projects, you already noticed that it's crazy. You can use BERT to train anything you want after a reasonable amount of iteration. You can train a model on textual data to give you whatever thing you want. Whereas to tell you, for example, in this guy's example, where was that company's pumped loop? See, it can tell you what kind of this feedback is positive or negative. It's about which aspect of my restaurant, for example. It's all done, and you only need a few training samples. You can see in this demo, they only need a few training samples. So this thing where you use a few training samples to get a customized language model, this thing is called few-shot learning. That's a buzzword of our time. And even crazier, sometimes you don't even need the few shot. You can do something called zero shot, which is called a pump. With no training at all, which means that this neural language model understands English, for example, so well, like a human being. Because you think about, if you're a human being, I can tell you to do something really easy, right? You don't need to learn English from scratch, right? You can quickly pick up to know how to do it, right? Because, for example, that demo, the zip code demo, the zip code demo, right? I can tell you to do it. You can immediately do it. You know what's a zip code in this address, right? Because you have enough knowledge already. So this case is called a zero shot, okay? And we will talk about all those creative things continuing on Thursday. Oh, one more thing. Thursday class is online because I will be staying home on Thursday, okay? All right. And so Thursday, don't come here, okay? I know you want to see me very much, but don't come here. Okay, all right. Thank you all. See you on Thursday over Zoom.